Welcome to my channel SK Vidyan Physics classes. I shall discuss some questions on semiconductor which are very important. First question is, a pure semiconductor has intrinsic carrier density of 10 to the power 20 per cubic meter at 300 Kelvin. When doped with impurity, hole concentration becomes 10 to the power 18 per cubic meter at 300 Kelvin. The impurity is pentavalent, trivalent. Value of electron density remains 10 to the power 20 per cubic meter. Value of electron density becomes 10 to the power 18 per cubic meter at 300 Kelvin. Now, when we say the intrinsic carrier density is 10 to the power 20 per cubic meter, that means the number of carriers, that is holes, as well as carrier density of electrons are same for intrinsic semiconductor. Now, when we dope a impurity, the hole concentration falls to 10 to the power 18 per cubic meter. That is, since the hole concentration falls, then electron concentration must go up. As a result, electrons will constitute as majority carriers, and the impurity is pentavalent impurities, and the material so formed is N-type semiconductor. We can also find out from the relation that carrier concentration for electrons, carrier concentration for holes, the product is equal to Ni square, where Ni is the intrinsic carrier concentration. So, carrier concentration for electrons after doping is equal to Ni square by Nh. This is 10 to the power 40 by 10 to the power 18. So, electron concentration is 10 to the power 20 per cubic meter. Hence, it is an pentavalent impurities. Second question is, trivalent and pentavalent impurities are added in equal amounts to an intrinsic semiconductor. The resulting semiconductor becomes intrinsic, N-type, P-type, and metal. Now the question is, when you add equal amount of trivalent and pentavalent impurities, the contribution to carrier concentration, that is the number of electrons and number of holes, rise equally, so that the carrier concentrations remains equal, and the material remains as the metal will be intrinsic semiconductor. So the correct choice is A. Next question is, the band gap in extrinsic semiconductor becomes smaller if the impurity concentration becomes high, the impurity concentration becomes low, independent of impurity concentration. Fourth choice, the impurity is pentavalent only. Answer is, the impurity concentration becomes high, so that the band gap in extrinsic semiconductor becomes smaller. Now, when we add impurity, if it is pentavalent impurities, then a donor label is formed. If it is trivalent, an acceptor label is formed. But when the impurity amount is large, that is, it is heavily doped, the intrinsic semiconductor is heavily doped, instead of an impurity label, an impurity band, that is donor band in N-type semiconductor and acceptor band in P-type semiconductor are formed, and as a result, the effective energy gap reduced both in N-type as well as P-type. And here the carrier concentration becomes greater than the quantum states available, and such a semiconductor so obtained is called a degenerated semiconductor and finds application in manufacture of tunnel diode. Next question. The conduction current in N-type semiconductor at 0 degree Kelvin is due to holes only, electrons only, both electrons and holes. No conduction takes place. Answer is electrons only. Now what happens? At 0 degree Kelvin, in case of N-type semiconductor, the donor level, which is close to conduction band, is filled, and the energy gap, the energy difference between the lowest level of conduction band and impurity level is to the tune of some few milli electron volt. As a result, when we apply an electrofield, the energy that is transferred to electron is sufficient to excite electrons from the donor level to conduction band. As a result, there is flow of current and it is due to electrons only. So choice B is correct. Out of the following materials, which is not a semiconductor? Silicon is a semiconductor, germanium is a semiconductor, gallium arsenide is a semiconductor called compound semiconductor, and sodium is not a semiconductor. Question number 6. Suppose the energy liberated in the recombination of whole electron pair is converted into electromagnetic radiation and the maximum wavelength emitted is 820 nanometer. The band gap we have to find out. Now consider this is the conduction band and valence band. When an electron from the lowest level of conduction band, lowest energy level of conduction band, combined with the uppermost level of holes in uppermost level of the valence band, the minimum energy is transferred in the form of electromagnetic radiation. So minimum energy means maximum wavelength, and this is equal to the energy difference, the energy radiated is equal to energy gap, and E is equal to h mu or hc by lambda maximum. Putting the value of h and c, it is 1242 electron volt nanometer, lambda maximum 820 nanometer, so it is 1.51 electron volt. Next question. A p-type semiconductor has acceptor level 57 milli electron volt. A p-type semiconductor has acceptor level 57 milli electron volt above the valence band. The maximum wavelength that can create a hole is, choices are given. Now this is the acceptor level and this is the valence band, and the energy difference is 57 milli electron volt. Now it is given the maximum wavelength that can create a hole. So maximum wavelength means minimum energy, that is h mu, can be greater than 57 milli electron volt or equal to. Since we have to consider the minimum energy, then h mu minimum is 57 milli electron volt or hc by lambda maximum equal to 57 milli electron volt. Now substituting the value of hc, that is 1242 electron volt nanometer, and the value of lambda maximum can be obtained. It is equal to 2.18 10 to the power minus 5 meter. So the choice is A. Now for a p-type semiconductor at 0 degree Kelvin, acceptor level is unoccupied, acceptor level is fully occupied, Fermi level is at the middle of energy gap, Fermi level is at the top energy level of valence band. Now, at 0 degree Kelvin, in case of p-type semiconductor, the acceptor level is unoccupied. Normally, the acceptor level in case of p-type semiconductor at 0 Kelvin is not occupied. And about the Fermi energy level, what happens? We know the expression for Fermi energy level EF equal to EB. EB is the topmost energy level of valence band, plus KT, K Boltzmann constant, T is absolute temperature, logarithmic of or ln NV by NA. NA related to concentration of doping, that is trivalent impurities concentration, and NV equal to 2 times 2 pi mH cross mH star KT by h square to the power 3 by 2. mH star is the effective mass of the hole. Now, at absolute zero temperature, that is T equal to 0, this term vanishes and Fermi energy level coincides with the topmost energy level in valence band. This is very important. Next question, similar question. For a n-type semiconductor at 0 Kelvin, donor level are all filled, donor levels are empty, Fermi level is at center of energy gap, Fermi level is at bottom energy level of conduction band. Now, for 0 Kelvin, at 0 Kelvin, for n-type semiconductor, the donor level is usually all filled, as in case of p-type semiconductor at 0 Kelvin, the acceptor level is empty, and in case of n-type semiconductor, the donor level is all filled. Now, what about Fermi level? Now, Fermi level EF given by is equal to EC. EC means the lowest energy level in conduction band, minus KT logarithmic of NC by ND. That is, ND refers to concentration of donor impurities, and if T equal to 0, then this term vanishes, then EF equal to EC. That is, Fermi energy level coincides with the lowest energy level in conduction band. Next question is, in a silicon crystal of n number of atoms, the valence band at 0 degree Kelvin is filled with 2n number of electrons, 4n number of electrons, 6n number of electrons, n number of electrons. To answer this question, let us analyze the electronic configuration of silicon. Electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p2. Now, there are 3s in an atom, there are 2 electrons, 3s 2 electrons, and 3p 2 electrons, and there are 6 quantum states in p orbital, and out of which 2 are filled. Now, in case of n number of silicon atoms, there will be 2n levels of 3s electrons, out of which 2n levels are filled, and there will be 6n quantum states, out of which 2n are filled and 4n are empty. Now, what happens when we bring n number of atoms closer to each other? A moment comes, a point comes, when these 8n quantum states levels will be distributed continuously distributed. Now, beyond this point, that is, if you further go on decreasing the distance, That means at this point there is no energy gap. If you go on further decreasing the distance between the atoms, when the atoms distance between the atoms attain the equilibrium separation as in case of crystal, then what happens? The number of field states get separated from number of on-field states. There are 4n on-field state and 4n field state. When the separation takes place, leaving an energy gap, we call this gap as forbidden energy gap, and conduction band is formed, valence band is formed. So, in valence band, there are 4n number of electrons, and in conduction band, there are 4n number of levels, states, which are on field, and in valence band, these 4n levels are filled by 4n electrons. So, the correct answer is 4n number of electrons. Now, this is the end of semiconductor discussion. I have discussed around 45 to 46 questions on semiconductors, and in next video I will discuss electronic devices, that is semiconductor devices. Thank you.